Hello everyone, and welcome. I'm excited to kick off today's presentation on oxidation ditches. This is part of the Wastewater Technology Fact Sheet series. We'll be exploring a proven biological treatment process that uses long solids retention times to effectively remove biodegradable organics from wastewater, all through modified activated sludge technology. Over the next few slides, we'll cover how this process works, its benefits, and where it's typically used. So let's get started. An oxidation ditch is a type of biological treatment process, but it's a bit of a modified version of the activated sludge system. What makes it unique is that it uses long solids retention times, or SRTs, which helps in effectively removing biodegradable organics from wastewater. These systems are usually designed as complete mix systems, meaning the contents are well mixed, but they can also be modified to operate more like plug flow systems, which have a different flow pattern. Typically, treatment systems like these consist of one or multiple channels arranged in a ring, oval, or horseshoe shape. Because of this shape, they're often called Racetrack-type reactors. To keep the system moving and ensure proper oxygen transfer, aerators are installed either horizontally or vertically. These aerators circulate the water, introduce oxygen, and aid in aeration, which is critical for the biological processes to work effectively. Connecting all of these points, the oxidation ditch is a versatile and efficient way to treat wastewater, especially because of its ability to retain solids longer and adapt to different flow conditions, making it a valuable part of the overall wastewater treatment strategy. Let's walk through how this process works. First, we have preliminary treatment, which involves removing large debris and grit using bar screens and grit removal devices. Sometimes, facilities also do primary settling at this stage, but that's not always the case. Next is aeration and mixing. Here, the flow enters the oxidation ditch, where it's aerated and mixed with return sludge from the secondary clarifier. Surface aerators help circulate the mixed liquor at speeds between 0.25 to 0.35 meters per second, ensuring proper mixing. Then comes biological treatment. This is where microbial growth occurs, thanks to the oxygen entrained in the mixing process. The goal is to promote microbes that break down organic matter. The motive velocity helps ensure these microorganisms come into contact with the incoming wastewater for effective biodegradation. After that, we have clarification. The treated water is settled in a secondary clarifier, which separates the remaining solids. Depending on the water quality requirements, tertiary filters might be added for additional polishing. Finally, the process concludes with the final discharge. Disinfection is crucial here to eliminate harmful pathogens, and sometimes reaeration is needed before releasing the water into receiving waters. This entire process ensures we treat wastewater effectively before it's safely returned to the environment. Now, let's explore enhanced nutrient removal. Oxidation ditches can be operated to achieve partial denitrification, which helps reduce nitrogen levels effectively. One common method is the modified Ludwig-Hettinger process, or MLE, where an anoxic tank is added upstream of the ditch. This tank, along with mixed liquor recirculation, allows for higher levels of denitrification, making the process more efficient. Moving to the aerobic zone, autotrophic bacteria play a key role by converting ammonia nitrogen first into nitrite nitrogen and then into nitrate nitrogen. This step is vital for nitrogen removal. The recirculation process involves taking mixed liquor from the aerobic basin and sending it back to the anoxic zone. This recirculation supplies the anoxic zone with high concentrations of nitrate nitrogen, which is essential for the next stage. In the anoxic zone, heterotrophic bacteria step in to convert nitrate nitrogen into nitrogen gas, which is then released into the atmosphere. This is how we effectively remove nitrogen from the wastewater. Additionally, to target phosphorus removal, an anaerobic tank can be added before the ditch. Some manufacturers have developed advanced modifications that cycle between anoxic and aerobic states, further enhancing nutrient removal capabilities. All these processes work together to improve overall treatment efficiency, aligning with our goal of achieving cleaner, environmentally friendly wastewater management. Let's take a look at where this oxidation ditch technology can be applied. As you can see, it's a fully proven secondary wastewater treatment method that works well in any situation where activated sludge treatment is suitable. This means it's quite versatile, especially effective in small installations, small communities, and even isolated institutions. One of the key advantages is its applicability in plants that require nitrification, which is the process of converting ammonia into nitrate. The basins can be sized with the right solids retention time, or SRT, to achieve nitrification even at lower temperatures, which is crucial for maintaining consistent treatment performance. Interestingly, this technology originated in the Netherlands, with the first full-scale plant installed in Voorschoten back in 1954. Since then, it has gained widespread acceptance. In the United States alone, there are now over 9,200 municipal oxidation ditch installations, demonstrating just how reliable and scalable this process is. And when it comes to nitrification, these systems are highly effective. They consistently achieve ammonia levels below 1 milligram per liter, which is a key indicator of successful nitrogen removal. This consistent performance is a testament to the robustness of the oxidation ditch process and its importance in modern wastewater treatment. Let's take a look at some of the advantages and disadvantages of this treatment process. Starting with the advantages, one of the key benefits is reliability. Because the water level remains constant and there's continuous discharge, this helps lower the overflow rate at the weir and prevents periodic surges of effluent. This consistency makes the system more stable overall. Another advantage is shock load protection. The long hydraulic retention time combined with thorough mixing means the process can handle sudden loads or hydraulic surges without being overwhelmed. This resilience is crucial for maintaining treatment performance under variable conditions. Additionally, this process produces less sludge compared to other biological treatment methods. The extended biological activity means bacteria and microbes work more efficiently, reducing sludge accumulation. That's not only good for operational costs, but also for reducing the environmental footprint. Energy efficiency is another major plus. Because the process requires less energy than some other biological treatments, it can lead to significant cost savings over time. Now, moving on to the disadvantages. One challenge is the quality of the effluent. The suspended solids concentrations tend to be relatively high compared to other modifications of the activated sludge process. This means additional treatment steps might be needed to meet strict discharge standards. Another consideration is land requirements. This process typically needs a larger land area than other activated sludge options, which can be a significant factor, especially in urban or suburban settings where land costs are high. Acquiring the necessary space can become quite costly in these environments. So, while there are clear advantages in reliability, shock load handling, sludge production, and energy efficiency, it's important to weigh these against the higher land requirements and the effluent quality considerations. Let's take a closer look at some of the key design parameters for wastewater treatment systems. First up is solids retention time, or SRT. The SRT values we use in design can vary quite a bit, ranging from as low as 4 days to over 48 days. Typically, for nitrification processes, we're looking at SRTs between 12 and 24 days, and this largely depends on the minimum mixed liquor temperature. Longer SRTs generally promote better biological solid stability and treatment efficiency. Next, we have BOD loading. This refers to the amount of biochemical oxygen demand that the system needs to handle, and it can vary widely, from less than 160,000 mg per 1,000 liters up to more than 40 million mg per 1,000 liters. However, a common design rate we often use is around 240,000 mg per 1,000 liters per day. This helps ensure the system can handle the expected organic load effectively. Moving on to hydraulic retention time, or HRT. In oxidation ditches, which are a popular treatment method, the HRT typically ranges from about 6 to 30 hours. The goal is to give the wastewater enough time for biological processes to occur without unnecessary tank volume. Speaking of oxidation ditches, they are usually built with reinforced concrete, but other materials like gunite, asphalt, butyl rubber, and clay have also been used successfully. The RAS recycle ratio, which indicates how much return-activated sludge is recirculated, generally falls between 75 and 150%. And the MLSS, mixed liquor suspended solids, concentration, which is crucial for maintaining biological activity, ranges from 1,500 to 5,000 mg per liter. Lastly, oxygen transfer efficiency in these systems typically ranges from about 2.5 to 3.5 pounds per horsepower hour, which is important for optimizing aeration performance. All these parameters are interconnected and critical for designing an effective and efficient wastewater treatment system. Proven performance results. As fully demonstrated secondary treatment processes, oxidation ditch processes are highly adaptable for nitrification and denitrification. Performance data from 17 oxidation ditch plants, ranging from 0.1 to 12 million gallons per day, shows that these systems consistently achieve over 90% removal of BOD, suspended solids, and ammonia nitrogen. Let's take a look at some real-world examples. The Casa Grande water reclamation facility in Arizona began operation in February 1996. It's designed to treat about 15,142 cubic meters per day, or 4 million gallons per day. Notably, it uses an anoxic zone before the aerobic zone to enhance denitrification, which is key for nitrogen removal. Another example is the Edgartown wastewater treatment plant on Martha's Vineyard. It's designed to treat 757 cubic meters per day in winter and up to 2,839 cubic meters per day in summer. This plant features 2 carousel Dennett IR basins, which help efficiently remove nitrogen during seasonal fluctuations. These examples highlight how oxidation ditch systems deliver reliable, high-performance treatment, adaptable to different flow rates and specific treatment needs. This flexibility and proven effectiveness reinforce their role as a reliable solution in secondary treatment. Let's take a closer look at the operation, maintenance, and costs associated with oxidation ditches. First off, they are known for their low maintenance needs. Compared to other secondary treatment processes, oxidation ditches require relatively little upkeep. In most cases, you won't need chemicals, although adding metal salts can help improve phosphorus removal if needed. When it comes to residuals or sludge generated, we're typically looking at production levels of about 0.2 to 0.85 kilograms of TSS per kilogram of BOD applied. On average, it's around 0.65 kilograms of TSS per kilogram of BOD, which is actually less than conventional activated sludge systems because these systems operate with longer solids retention times, or SRTs. Oxygen requirements are another important aspect. Usually, the oxygen needed ranges from about 1.1 to 1.5 kilograms of O2 per kilogram of BOD removed. For TKN oxidation, it's approximately 4.57 kilograms of O2 per kilogram of TKN. Transfer efficiency, which measures how effectively oxygen is transferred into the water, typically falls between 2.5 and 3.5 pounds per horsepower hour. Now, looking at capital costs, for facilities treating anywhere from 3,785 to 25,740 cubic meters per day, equivalent to roughly 1 to 6.8 million gallons per day. The costs generally range from about 66 cents to $1.10 per liter per day, or $2.50 to $4 per gallon per day. A good reference point is the Blue Heron Water Reclamation Facility in Florida, which, at 4 million gallons per day, was built at around 80 cents per liter per day. Finally, on the operating costs front, oxidation ditches are quite economical. They tend to have significantly lower operation and maintenance costs compared to other secondary treatment options. Energy use is low, operator attention is minimal, and often no chemicals are needed. For example, the Tar River facility reported about 40% energy savings when compared to conventional activated sludge plants, which really highlights how efficient and cost-effective this system can be. When considering a wastewater treatment solution, reliability and proven performance are key. Oxidation ditches have been around for a long time and are a mature technology, with over 9,200 installations across the United States. This extensive use demonstrates their dependability. They consistently achieve more than 90% removal of BOD, suspended solids, and ammonia nitrogen, which are crucial for meeting environmental standards. Plus, they offer significant operational advantages, making them a trusted choice. Another important aspect is energy efficiency. These systems can save up to 40% of energy compared to conventional treatment methods, which not only reduces costs, but also minimizes environmental impact. They're designed to be low maintenance, requiring minimal operator attention and fewer chemicals, which simplifies operations and lowers ongoing expenses. Flexibility is also a major benefit. Oxidation ditches can be adapted for various treatment processes like nitrification, denitrification, and phosphorus removal, allowing them to meet different treatment needs. And finally, their proven results speak for themselves. Consistent performance across a wide range of applications, reinforcing their status as a reliable, cost-effective solution for wastewater treatment.